and welcome everybody to the Math 286 Exam 3 review. So we had a request for number 6 from the review sheet. And I'll just repeat that this Exam 3 is going to cover about 4 sections. 4.6 is variation of parameters. 4.7, which was Cauchy-Euler equations. 5.1 were harmonic motion spring problems, and then 7.1, some basics of the Laplace transform. Now problem number 6 is a non-homogeneous Cauchy-Euler equation. Okay, so let's see how that's solved. It's x, and I'll have to toggle back and forth to write this down, but we have x squared y double prime, so this is number 6, x squared y double prime minus 3x, oh no, that's number 5, minus 4x y prime is 4x y prime plus 6y equals natural log of x squared. Plus 6y equals natural log of x squared. Okay, so we want to use variation of parameters to solve this non-homogeneous equation. But first we're going to find the auxiliary equation in order to get the solutions to the associated non-homogeneous. So the associated non-homogeneous Cauchy-Euler equation, it has the same left side, but then everything's equal to 0. And I'll just write the polynomial, so that's going to be m times m minus 1. Remember that the first term gets replaced not with m squared, but m times m minus 1 times whatever coefficient might have been over here. Then we have minus 4 times m plus 6 equals 0. Or if you remember that the shortcut here is this middle coefficient of m becomes b minus a, that's, you can use that as well. So we have m squared minus m minus 4m plus 6 equals 0. So this is m squared minus 5m plus 6, and we get our two values of m. This is cleanly factored as m minus 2 times m minus 3. So we have two m's. So the complementary solution would be c1 x to the second power plus c2 x to the third power. And now we have to use these two x squared and x cubed solutions that are y1 and y2 in the variation of parameters formula, because this is non-homogeneous. We have this natural log of x squared. Okay, so I'm going to just go back to the Hangout, see if there are any questions so far. Everybody with me? And how is the resolution of the writing? Is it clear? Okay. So going back, what do we have? Well, we're going to have to find the wronskian, and then our non-homogeneous term is natural log of x squared. But before we deal with that, let's go ahead and recall that variation parameters involves variable coefficients, coefficients that are functions, and then we have our y1 plus u2, y2, where y1 is going to be this x squared, y2 is x cubed. You can swap these, it doesn't really matter. This doesn't have to come first before x cubed, but just make sure you're consistent. And so we'll need our wronskian, that's part of the variation of parameters formula. So I have x squared, x cubed in my first row. The second row are the derivatives. I have 2x and 3x squared. Now when we cross multiply, we're going to have 3 times x squared, it's 3 times x fourth minus 2x times x cubed minus 2x to the fourth. And that simplifies to x to the fourth. You notice in particular, when x is positive, this is non-zero, and when x is negative, this is non-zero. There is a zero here at 0, but since this is Cauchy-Euler, x equals 0 is a singular point. So if we were specifying a domain, or if we had initial conditions, it'd have to involve an interval where x is strictly positive or strictly negative. Oh, before I forget that wronskian, let's have a look at that again. X to the fourth. Okay, so now we're going to use variation parameters. We have u1 prime u1 satisfies a differential equation where we have fraction w1 over the wronskian. What was that? X to the fourth. I just want to double check that. Yeah, x to the fourth. Good. And now we have to find that w1. W1 looks like the wronskian, but we replace the first column with 0, and then our non-homogeneous function, natural log of x squared. Natural log of x squared. And then the second column is the same as the wronskian second column, which was x cubed over 3x squared. So we have x cubed 3x squared. That's w1, and then we're going to divide by that wronskian x to the fourth. And what does this simplify to? 0 times 3x squared minus natural log of x squared times x cubed. So we have, I'll write the x cubed first. Oh, don't forget the minus sign. Natural log of x squared. And then we're dividing by x to the fourth. So we simplify this, some powers of x cancel, and we get negative natural log of x squared over x. Okay, now this x squared, you can leave it as it is, but this problem will be a little bit easier if we use power of logs and bring that 2 down. Oops. So this is going to be equal to negative 2 natural log of x over x. And remember, that's what u1 prime is. So to get u1, we integrate this, and the integral here is just a u substitution problem. We have the integral of negative 2 natural log of x over x. And because I have this x in the denominator, that's really my derivative of the natural log. Oh, I'll write the dx there too. So I could rewrite this setting up a u substitution problem. So it's negative 2 natural log of x dx over x. And this dx over x, that's going to be my du, where my u is the natural log. If u equals natural log of x, then du is 1 over x dx. Okay, and so the antiderivative now is clearly minus u squared. And we don't have to worry about the plus c. So this is the natural log of x for u, so we have negative the square of the natural log. And that's u1. So now we move on to u2. Oh, didn't quite leave myself enough space. Let's find that u2. So u2 prime, now we need that wronskian looking fraction. But I guess w2 is part of a determinant. The w2 over the wronskian, w2 is this determinant of the first column of the wronskian, x squared 2x, x squared 2x. But now over here in the second column we have 0, and then our natural log of x squared term. All over x to the fourth. And don't forget to put the x to the fourth. The integration can end up being unbearably difficult if you accidentally forget the w part. That's a common mistake. So here we have x squared times natural log of x squared times, and then you can just make that 2 natural log of x, just like we did before, over x to the fourth. Okay, so this simplifies to 2 natural log of x over x squared. Okay, this looks a little bit harder than before if I did everything right. It's not as straightforward as this u substitution because basically now we have an x squared in the denominator, so this might have to involve some kind of integration by parts. Before we move on though, any questions in that problem? Oh, I'm getting a question. Is it possible to zoom out on my whole screen so we can see the whole problem? I can do that now, but not while I'm writing because it makes it harder to write clearly. And now that I've run out of space, I think I'm going to have to delete some stuff. But before I delete this, we just started off with number 6. We found the auxiliary equation, and to find the complementary solutions, and they're built up from x squared and x cubed. We use those to find the wronskian. We use our variation parameters formula. u1 prime is w1 over x to the 4th. And then we did the integration to find u1 is negative natural log of x squared. Remember, this is where we're going ultimately. Our solution is going to be a sum of yc plus yp. And we found u1. The only thing left in this problem is u2. So let's go ahead and do this integral. Okay, and I think I just pulled this problem from the textbook. So if this integration ends up being a little bit harder, that's not really. I'm not looking to put difficult integration on the exam. Maybe something that is at hardest it would be integration by parts, like once, but it would be an obvious integration by parts. I'm mostly wanting to make sure that you know how to do differential equation solving. I'm not trying to revisit calculus. So I'm a little bit nervous this is going to be messy, or at least take a little bit more work than I have here in this space. But let's give it a go. Okay, so we have what was that? The integral is going to be 2 natural log of x over x squared. Okay, so u okay, pen. We have u2 prime is 2 natural log of x over x squared. Okay, so if we so just playing around with a few things, if we were to do a u substitution with natural log of x, then du is 1 over x dx, and then this integrand, this integrand in our integral would end up being 2u du, but then we'd still have 1 over x left over, and then we'd have to rewrite this x in terms of u, so some kind of back substitution. We can write e to the u power equals x. That follows just from this substitution, but that may not be as helpful. Or at least it'll tell you where to go next. So this would be 2u e to the negative u. If x equals e to the u, 1 over x is 1 over e to the u, or e to the negative u. Okay. So if you do it this way, we clearly have to do integration by parts. Differentiate this u and integrate this e to the u. Okay, so let's go ahead and work this problem that way. So I do a u substitution to convert the integral in terms of natural logs to this one that has 2u e to the negative u du. And now I want to differentiate this u and integrate this e to the u. So integration, well, let's stop using this line actually. Let's rewrite this as u2. So I'm doing the integration now via integration by parts. I have 2u minus e to the minus u. Remember, I want to integrate this. So this is my 2u and my integral of e to the negative u minus, I don't want this to get cluttered with previous work. Okay, so there's a little boundary, minus the integral of the derivative of 2u, that's just 2, times this antiderivative e to the negative u, again that's that negative e to the negative u du. Okay, so this is like my uv minus my integral v du in the integration by parts formula. And so now I just have to integrate this. I have minus 2 from here, minus 2u e to the negative u, minus, and then there's a minus here, so that's plus 2 times the antiderivative e to the negative u. So I'm going to get another minus sign. And we don't have to worry about plus c. Okay, so in the end we found u2 is this expression. But remember, let's put our u as natural log of x. That was what u represented. It's minus 2 natural log of x e to the minus natural log of x. And we can simplify this, of course, which we will do. Minus 2 e to the negative u, natural log of x. And so then this simplifies to, well, if I want to have the natural log and the e undo each other, I first have to bring this minus sign as an exponent. So this whole thing right here is 1 over x. So I have minus 2 natural log of x over x, and this is negative 2, 1 over x, minus 2 over x. So here's my expression for my u2 parameter. And let's go ahead and rewrite the solution now. Remember, I'm just taking the sum of yc plus yp. Okay, so I'll go ahead and just erase this to create some extra space. Need a little more. Okay, so we have all the ingredients. I'm just going to summarize the answer. Y is c1 x squared plus c2 x cubed, plus we have our u1, which we found over here, negative natural log of x squared. Okay, so I'm going to change this plus to minus natural log of x, and that whole thing's being squared, the whole natural log, not just the x, times x times y1, which was x squared, plus our u2, which we just found, and it's got some minus signs, so I'll just pull out a minus sign and write that as natural log of x over x plus 2 over x times y2, the second function, x cubed. Okay, so this is the final answer. What's that minus sign there from? I think that was just straight mark. Okay, so just some tips. This may not be simplified fully, but on the test, I'm probably not going to ask you to simplify it, especially if a problem involved this much integration or some integration by parts. If it was very easy to do, maybe I'll ask you to simplify it. What does simplifying entail? Well, if we did do some algebra and end up with any terms from here or here that look like a constant times x squared or a constant times x cubed, then those terms can be absorbed effectively into these. And you don't really show the absorption, you just choose not to write them. For example, look at these last two terms. 2 over x times x cubed. If we distribute the x cubed, that's going to look like 2 times x squared, or technically we have this minus sign over here, so it's minus 2x squared. That's really part of c1x squared, and so a simplified answer can just ignore that part. Now, these natural logs, they're going to stick around. When you multiply these x cubes, you're going to have like negative natural log of x squared, minus natural log of x squared, or minus natural log squared of x squared. Those terms have nothing to do, they don't look like a constant times x squared or a constant times x cubed. Now, and sometimes when you have sines and cosines, you can do more simplifying using trig identities, like using sine squared plus cosine squared equals 1, and you saw some problems from the homework like that. Okay, so going back, any questions? Is that good? And if you have a microphone enabled, feel free to interrupt me with any questions or interrupt if in the chat room if there are. Otherwise, I'll move on. So this one is probably requested just because of that messy integral U2, that's my guess. What other kind of problem? Is there a particular number from the review sheet you'd like to see, or any topics? Again, we have the Laplace transform, its definition, and some basic computations using the definition. We have some 5.1 problems, harmonic motion. We have Cauchy-Euler, which we just did Cauchy-Euler, and we did variation parameters. So that was a nice review of the 2 sections before. I hope that the screen was zoomed out, or that the writing was readable enough. Any other questions? Number 7? Sure. Okay, so what I will do is I'll try to write things a little bit more organized so that we don't have to delete things, because I would also like to save some of this work and export it as a file so that if you need to see it. So let's go back to the drawing board and go ahead and save this file first of all. Some people might find the integration useful. Whoops. Okay, so let's export that, and then we'll move on to number 7. So this was number 6. Okay, so let's start fresh. Number 7, what do we have? I'm going to switch over to the review sheet. Number 7, we have a harmonic motion problem. Mass weighs 32 points. Clearly that's a typo on my part. I think I was looking at that other word, that other P word. That should be pounds. That would be the most reasonable unit, especially since we're seeing feet elsewhere. So 32 pounds is the weight, and it stretches a spring 8 feet. The mass is initially released from rest. So that tells us that our initial velocity would be 0. We're releasing it from a point 4 feet below the equilibrium position. But remember, below corresponds to a positive displacement. That's how we're orienting our vertical axis. And the subsequent motion takes place in a medium that offers no damping force. Find the equation of the motion if the mass is driven by an external force equal to F of y equals e to the negative t. And that y is also a typo. It should be f of t. Pardon me. So let's rewrite the differential equation for the problem I just described. We have, let's go ahead and first just write this in terms of Newton's law. We have mass times acceleration, the mass times acceleration, which will be denoted x double prime, and then we're going to have a sum of forces. And in this one, we only have an external force and a force from Hooke's law, but there's no damping force. So the force from Hooke's law looks like negative k times x, and we haven't divided by m yet. And remember, the negative sign is there because this is a resisting force that counteracts the acceleration due to gravity. And then we also have a external force e to the negative t, I think it was. So we'll check the file. External force equal to f of t equals e to negative t. Okay. So first of all, we have to figure out that k, and k is is obtained by writing Ks equals mg. This is what our equilibrium condition is. The force due to gravity, or the weight of the mass, is counterbalanced by the spring's tension. So in this problem, we're told what S is. I think it was 8 feet. Yeah, 8 feet, and the weight is 32. Okay, so this mg is 32 pounds, not points, and S is equal to 8. So K8 equals 32, so K is equal to 4. And when we write the differential equation, we're going to divide through the whole term by m. So let's figure out m. Here, since we're using feet, then we're also using g as 32, and as opposed to 9.8 because of our units. So the mass is going times 32. That's our g constant, equals 32. So the mass is just 1. Okay, so nothing really to divide through. Our differential equation then is x double prime equals, let's bring everything to the left side. Adding over my k, so that's 4 plus k times x, and we'll leave the external force over on the right side, because this is thought of as a non-homogeneous term. So we have the second order differential equation. Its related auxiliary equation would be m squared plus 4 equals 0. So we get 2 imaginary roots plus or minus 2i. So this motion is going to be C1, we have a cosine and a sine. Cosine 2t plus C2 sine 2t. And then we're also getting a particular solution to the non-homogeneous. So these two terms, that's our complementary solution. It's that they are solutions to the associated homogeneous equation. If we had no external forces, if this exponential was missing, just equal to 0, then we'd be done. But right now we have this non-homogeneous external driving force, and that's, we have to use that to compute a particular solution. So we can use either variation of parameters or undetermined coefficients. I'm going to keep things simple and brief just by using undetermined coefficients. We have some e to the negative t. So our guess for the particular solution would be some constant times e to the negative t. But we have to check if there's any redundancy. Does this guess cause redundancy between any terms in our complementary solution? No, that's an exponential. It's not a cosine 2t. It's not a sine 2t. So we don't have to multiply this by any t's. We just work with that guess. And so I'm going to plug this a e to the negative t into x double prime plus 4x equals e to the negative t. So what's the second derivative? Well, before I can do that, I have to take the first derivative. That tells me that the second derivative is bring another negative sign out using the chain rule. So now I have to take the sum, or almost the sum, but there's a 4 there. The second derivative is a e to the negative t plus 4 times the original function, 4 times x. So that's e to the, whoops, I need my a e to the negative t. And this equals the right side, just 1 times e to the negative t. And so I get this equation. My coefficient becomes 5, because I have a plus 4a, so 5a e to the negative t equals 1 e to the negative t. That tells me that 5a equals 1, or a equals 1/5. Okay, so now I know my particular solution, so I can summarize the whole solution, which is we have C1 cosine 2t plus C2 sine 2t plus 1/5 e to the negative t. And I'm not quite done because I have initial conditions. Remember that the spring started at rest, so x prime equals 0. And what was the initial displacement? I've forgotten that. Let's go back and read. The mass is initially released from a point 4 feet below the equilibrium position. Okay, so 4 feet below would mean x of 0 equals a positive 4. Below is positive, above the equilibrium position would be negative. So first of all, plug in 0. When I do that, cosine of 0 is 1, so I just get C1, and sine of 0 is 0. But I also have this term. So this is why I didn't use my initial conditions until the very end, because I do need my particular solution. And so I get plus 1/5. E to the 0 would be 1. So C1 plus 1/5 equals 4. It's plus 4. And that tells me that C1 is 4 minus 1/5, or 20/4. Take that back. I mean fifths, 20/5 minus 1/5 is 19/5. Okay, now to find C2, I first have to use this derivative. So x prime, I have to compute that. That's going to be negative 2 C1 sine negative 2 C1 sine of 2t. Of course, I know C1. I could substitute that in now if you care to. Plus 2 times C2 cosine plus 2, and I'm running out of room. Let's write that down here. Plus 2 C2 cosine 2t. Taking the derivative of that second term using the chain rule. And derivative of this last guy is negative 1/5. So minus 1/5 e to the negative t. Now we plug in 0 and set that equal to 0. So 0 equals, plugging in 0, sine of 0 is 0, this goes away. Cosine of 0 is 1, so we get 2c2 minus 1/5. So that tells us that c2 equals, bring the 1/5 over, divide by 2, looks like it's 1/10. So we have our constants. If you have room, which you would on an exam, I would just rewrite the solution with these constants. 19/5 is C1, C2 is 1/10, and basically just rewrite the solution with those constants there. But I think I'm out of space, so just leave my answer that way. Anyone have questions? Going back to any questions at all for number 7? So you, if there's no external force, then you're just solving some second order linear constant coefficient differential equation. You're going to solve some kind of quadratic, and in the test you might be given an external force, or you might be giving a damping force, so that the damping force might change what kind of equation you have. If you don't have any damping, you're just going to get cosines and sines. You're going to have an auxiliary polynomial with imaginary solutions. If you have an external force and you're lucky, then you can use undetermined coefficients, but you might have to do variation of parameters. And again, don't worry too much about the integration here. You have to do it, but I'm not going to give you anything terribly difficult. At most, it would be integration by parts once, or use substitution. So what should our next problem be? We've done a spring one. We did that Cauchy-Euler problem that was not homogeneous, and so we also had to apply variation of parameters.
Could you do question 2?
Question 2? Sure.
Yeah.
Thank you. Let's save. I'm going to export this first. 7. Okay. So number 2, what did that say? Just flipping back to the review sheet.
Use variation of parameters to solve y double prime plus y equals cos square x.
Yeah, so number 2. Number 2, we have y double prime plus y equals cosine squared x. I think that's it, right?
Yes.
So this is not homogeneous. We first have to solve the associated homogeneous equation. So if I had just y double prime plus y equals 0, I would then write the auxiliary equation m squared plus 1 equals 0. So m is plus or minus I. So that tells me that my complementary solution y sub c, c1 cosine x plus c2 sine of x. And now I'm most likely either going to do undetermined coefficients or variation of parameters. Those are really the only 2 methods we learn for solving non-homogeneous equations. Unfortunately, this is cosine squared, so undetermined coefficients isn't available, which means we have to use variation of parameters. So let's go ahead and calculate this discriminant. The wronskian. Yeah. So this cosine x is my x1 or my y1. Sine x is my y2. So I'm going to have cosine x, sine x, and then the derivatives in the second row, negative sine x, cosine x. And due to the Pythagorean theorem, this is cosine squared minus negative sine squared. So our wronskian is just 1 in this problem. So now we write our differential equation for u1. Remember, this is the variation of parameters formula. This is w1 over the wronskian. Wronskian is just 1, but what I need more space for my w1. w1, it has first column 0 and cosine squared x, that non-homogeneous function. So we have a cosine squared x here. And then the second column is the same, sine x, cosine x, sine x, cosine x, divided by 1. Okay, so I've divided by 1. And this equals 0 times cosine x minus sine times sine x cosine. Sine x cosine squared x. Okay, we recognize sine is the derivative of cosine, so when we have to find u1, we integrate and we'll use u substitution. So u1 is going to be the integral of, so letting u be cosine, then this is going to be negative. Oh, I just occurred to me I left off a minus sign. When I do the determinant here, 0 times cosine minus cosine squared sine. So there should be a minus sign here. Let's get that minus sign from the determinant computation. Okay. And the minus sign here was right here was actually from the derivative, but let's go ahead and do. We have cosine squared. We have cosine squared x, and then I'm going to bring that minus sine x right here, because this is really du when u is cosine. Derivative of cosine is a negative sign, so that negative should follow the sine x and the dx. So this looks like the integral of u squared du, which would be 1/3 u cubed. So let's write that up here. So u1 equals 1/3 u cubed. And we don't have to write the plus c. So this equals, what was u? Cosine x Okay, and now we have to find our U2. So U2 prime is W2 over the wronskian, and again the wronskian is just 1, so let's just write W2. This is our first function, our y1, which was cosine, and then we have negative sign, but now we replace the second column of the wronskian with 0 cosine squared. So this is going to be cosine x, negative sine x, 0 cosine squared x. And now we multiply that out. This is cosine cubed. Okay, and this is why I gave you the hint. I said that I gave you the antiderivative of cosine cubed. It involves, what was it? I think, integration by parts or a trig identity. So it's one of those messier ones from Calc 2. So let's use that result. U2 is, and I have to go to the hint. Don't know it off the top of my head. The hint was the antiderivative of cosine cubed is 1/3 cosine squared x sine x plus 2/3 sine x. And we don't have to worry about the plus c. So 1/3 cosine squared sine 1/3 cosine squared x sine x, and what was the other part? Plus 2/3 sine x plus 2/3 sine x. Okay, so that's U2. And now I'm going to have all the ingredients for my solution. It is the complementary, which I wrote down previously, linear combination of cosine and sine, plus my particular, which is, it looks like a linear combination, but the coefficients C1, C2 get replaced with these U1 and U2 functions. U1 is 1/3 cosine cubed, U2 is this sum. So let's go ahead and fill all that in. Our solution is C1 cosine x plus C2 sine x. Now, plus the particular, our U1 was 1/3 cosine cubed, 1/3 cosine cubed x. Then I multiply by my first y1 function, cosine x, plus U2, which is this stuff, so I have to include some parentheses because it's all going to get multiplied by sine. And running up against the, ran out of space. Sine x is being multiplied by all the stuff in parentheses. Okay, so it's possible that there's some simplifying that can be done here. Just like the last variation of parameters problem, if you do some algebra and you're able to write any terms by themselves as a constant times cosine x, then this first term can absorb it, or if any of this stuff simplifies to a constant times sine x, then you can delete those terms. So there's probably some kind of sine squared plus cosine squared floating around here for us. I'm going to skip that though, and in the test I'm not going to worry so much about getting a simplified answer, so I'll just leave that alone. But this part here can probably be simplified. You can probably pull out a sine squared plus cosine squared. Okay, so any questions? Anybody?
Could you just tell me which questions you already went over? Because I had trouble getting.
Sure. So some people are requesting problems in the group chat, but I believe that you don't see the previous posts until you log in. So we started off doing number 6, we did number 7, and then that number 3. And then Brett asks if I'm going to post solutions to all the problems on the exam 3 tip sheet, and the answer is no. There are about 30 problems there. I don't have time to write out all the solutions. However, I gave you some tips that the solutions are for the textbook problems are all in the back of the book, or I mean the odd number ones. And then also, if you just want the solutions, you can type this into Maple or Wolfram Alpha and find the answers. So there's really not any tricky parts of the problems. The techniques are pretty straightforward. In Cauchy-Euler, you just have to know how to find the quadratic auxiliary polynomial and then find the roots, and solve non-homogeneous problems with variation of parameters. With variation parameters, the trickiest part might be integration, but the homework integration is going to be a lot more difficult than anything you'd see on the test, so that's shouldn't be too much of a concern. And then 5.1, harmonic motion. 7.1 problems are going to be very straightforward. Use the definition of the Laplace transform to calculate some basic Laplace transforms, like the ones we did in class. So there's nothing too tricky here. It's mostly just reviewing the textbook. And if there are particular problems you have questions about, that's what I'm aiming to solve today.
Okay. Could you go over one of the 5.1 homework questions?
Homework question or what? Sure. Yeah, I could do a homework question. I don't have the homework, so I don't have that in front of me. Do you have a problem in front of you?
Yeah. It's a mass.
Let me export this really quick, and then as you read the problem to the rest of us, I'll go ahead and decode it into mathematics. Let me just export this file really quick. Yeah. And so we're going to do another harmonic motion one. Very good. Okay, so this is from homework. Do you have a problem number?
3.
3? Okay.
Yes.
Okay, so shoot.
A mass weighing 20 pounds stretches a spring 6 inches. The mass is initially released from rest from a point 3 inches below the equilibrium position. Find the position x of the mass at time t pi over 12. T equals pi over 12.
Okay, I missed the second initial condition. We're going to release this mass from rest. What was the position?
From a point 3 inches below the equilibrium.
3 inches below. Okay,
yeah.
So that would be a positive 3 inches. Now, of G being most commonly expressed as 9.8 in what are those units called? SI units, or the book calls them engineering units when you deal with feet, which is 32 feet per second squared. We really have to translate inches into feet, so this would be 1/2 feet. Otherwise, we just deal with a less common G, but let's just use 32. So this is 3 inches is 3 over 12, 1/4 feet. And then all the other units I think are okay. So our weight was 2 pounds. That's not 21, it's 2 lb, 2 pounds. And that's going to be equal to k times s. That's the equilibrium condition for that relates weight due to gravity, or force due to gravity, which is weight, and the force from Hooke's law. So equilibrium is weight 2 pounds equals k times s. We're told s equals 1/2 feet, so that tells us that k has to be 4. So we get, I'll write that down here, 2 pounds equals s, which is 1/2 feet, times k. So the k in this problem is 4. Now we're not given any kind of damping force or from some surrounding medium, so our differential equation, starting with Newton's law, is mass times acceleration is equal to negative k times x. And I don't think we had an external force either, so this is it. You're welcome to write Newton's law, or you can just skip ahead and divide through by m. So when we divide through by m, we have -4. And what's the mass? Well, they didn't tell us exactly what the mass is. However, we do know that 2 is the weight, 2 pounds, and we're using 32 for G. So that tells us that m equals 2 over 32, 1/16 slugs. So we have to write divide through by 1/16 or multiply both sides by 16. It's the same thing. Times. So our differential equation is x double prime equals, let's bring this -4 over 1/16 x to the other side. So plus, and what's 4 over 1/16? That's 4 times 16, so that's 64. X equals 0. The auxiliary equation would be, let's not use m actually, because we're using mass for m, so I'll just use n. N squared plus 64 equals 0. The roots are imaginary, which we like because this is a spring, and so we should get springs. Oops, 8. We should get cosines and sines, which we get when our auxiliary equation's roots are imaginary numbers. So our solution looks like C1 cosine 8t plus some other constant sine 8t. Okay. And now we just have to determine these parameters. We start at rest, so x prime of 0 equals 0. And then at 0, what did we have? Positive 3 inches, which equals 1/4 feet, so a quarter. Okay, so plug in these conditions. When I plug t equals 0 directly into this formula, I end up getting cosine 0 is 1, and sine of 0 is 0. So I now have found C1. That's just 1/4. That's what will go in right here. And now before I plug in 0, I have to find the velocity. So x prime is, using the chain rule, -8 C1 sine 8t plus 8 C2 cosine 8t. And the 8's come out because of the chain rule. Now you plug 0 into this, and for t, and what goes away? Sine of 0 is 0, and we're left with 8 C2 times cosine of 0, which is just 1. So 0 equals 8 C2, so there is no C2. C2 is equal to 0. 0 equals 8 C2. So let's summarize the x. We just have 1/4 cosine 8t. This term went away. 1/4 cosine 8t. And now we weren't asked for the equation of motion, but we were asked for the motion of particular time value, pi over 12. So I'm going to plug in pi over 12 for your final answer. And that's 1/4 cosine of 8 pi over 12. What's 8 pi over 12? That simplifies to common denominator would be 4, so that's 2 pi over 3. So cosine 2 pi over 3, what quadrant does that reside in? 1 pi over 3, 2 pi over 3, this one. So cosine's negative. What is it, 1/2 or root 3 over 2? It's 1/2. Cosine 2 pi over 3 is -1/2, and that simplifies to -1/8. So that's the final answer in that problem. That represents the displacement from equilibrium of the mass at t equals pi over 12.
Okay.
Okay, so I'll export that now. Any questions about that problem? Anyone?
No.
So let's say that's homework 3. Okay, so we can do one more problem. What kind should it be? Are you guys comfortable with Laplace transform? Just make sure you know that the definition of that integral. It's an improper integral, which was a Calc 2 topic, so you have to know how to either you do U substitution or integration by parts to get the antiderivative, but then you have to evaluate it between 0 and infinity, and that involves a limit, although typically one of those limits will be 0. So I'll go through an example with the Laplace transform, unless there are any other things that you're just dying to do before. Anything? No? Okay, so let's do a Laplace transform problem. Let's find the Laplace transform of, let's see, what should we do? Let's do e to the 17t. Okay. So the definition would be the integral from 0 to infinity. We have e to the 17t, and then we have to multiply it by e to the negative st. We integrate with respect to t, that's going to get rid of the t variable and leave a function of s. Okay. So in a problem like this, I'd want you to use the definition, meaning if you know the shortcut, and some of you you did in the last class, you know it's 1 over 1 or s minus 17. Don't just write that. Actually do the integration directly. So to integrate this, we're going to combine these exponentials. So it's going to be e to the 17 minus s times t. So this is a u substitution problem. I just let u be this 17 minus st. U equals 17 minus s t. And we're treating s like a constant. So du is just 17 minus s dt. So the antiderivative then is going to be 1 over 17 minus s times e to the 17 minus st. But we need to evaluate this from 0 to infinity. And since, I'll remind you, it's t goes from 0 to infinity, leaving s alone. Okay, so what happens? Well, we have, if you want to write this as a limit, that's fine, although it's okay if you don't. We're first going to plug in m. So this for t, so 1 over 17 minus s, e to the 17 minus s times m, and minus, now we're going to plug in 0. 1 over 17 minus s, e to the 0. Okay, so now this stuff is all going to go, this stuff right here is going to go to 0. That does require on 17 minus s. 17 minus s would have to be negative. So this term goes to 0 when 17 minus s is negative. And now this becomes just negative 1 over 17 minus s, or you can take that negative sign and flip the order of the denominator, so s minus 17. So that's the derivation there, looking for something like this. If this problem had been on the exam. Okay. So any final comments, questions, anybody? Brett asks to do number 12. Sure. Okay, and I think this will be the last one.
You just did it.
Number 12. Oh, Oh, maybe he asked before I did it, and then that's funny. I was reading your mind, Brett. Okay. Well, so one more problem then.
Okay. Alright, can you do a Cauchy-Euler equation?
Yeah, we'll do Cauchy-Euler. Let's see. So let's one of the ones from the review sheet. What do we have? Let's do non. Oh, there's only one non-homogeneous one on the exam. Just to beef this problem up, so I'm showing you how to do variation of parameters. I'm going to take number 4 and modify it. So I'm going to add a non-homogeneous term. Number 4. So here's a 4. Let's use white. 4 variant. Number 4. Let's write that. Is 2x squared. I'll just remember the coefficients. 2, 2, negative 8. Okay. 2, 2, negative 8. So that's the, and I totally forgot my derivatives. Y double prime, y prime. Okay. And instead of having that be 0, let's try, I'll put an x here. Now it's very dangerous to be making up problems on the spot. I might lead you down some path of impossible or very difficult integrals, but that's okay. If it ends up being a hard integral, we'll just write it down, but not try to solve it. So the auxiliary equation would be 2 times m minus 1. We replace this first term with m times m minus 1, and the constant 2 just goes along with the ride. So if you write m squared instead of m times m minus 1, you're not thinking Cauchy-Euler, but you're thinking constant coefficients. But these x squared x terms here mean this is not constant coefficient. And we have minus 2m minus 8 equals 0. So this is the auxiliary polynomial, and we get 2m squared minus 2m minus 8 equals 0. Consolidating these terms, 2m squared minus 4m minus 8 equals 0. Okay, all these coefficients are even, so this is the solution set's equivalent to the solution set of m squared minus 2m minus 4. Okay. And what do we have here? Can this easily be factored? 4 has factors 2 and 2, but the minus sign would mean we would need a difference to be 2. So this actually doesn't, this is deceptive. Oops. Okay, so this isn't the auxiliary polynomial because I made a mistake here. This is plus, so I should have put a plus sign. But before I change everything, just keep in mind we'd have to use the quadratic formula here. You'd get imaginary roots, and then those imaginary roots involve cosines of x times natural log of an imaginary part. But here, let's go ahead and correct that. It's plus 2. So that makes this plus. Oh, that's nice, because then these two m's cancel out. So this is really 0 m. Okay, so making the correction here, just let's erase this. And that's a nice polynomial. M squared minus 4, difference of 2 squares. So m is plus or minus 2. Okay, so now let's write the complementary solution. Yc is some constant times x negative to the negative 2 power plus c2 x to the positive 2 power. And these two powers of x, these are y1 and y2. We need them for the wronskian. Okay. I could solve this using what's called undetermined coefficients, but instead let's practice variation of parameters, since that was one of the topics. So to find my particular solution, I'm going to write u1 y1 plus u2 y2. Remember, that's what it consists of. And u1 prime is W1 over the wronskian. Let's find the wronskian. And I have to use that twice. Let's do that up here. Wronskian is x to the minus 2, x squared. And then here I write the derivatives. So we have negative 2 x to the minus 3 and 2x. For my own sanity, I'm going to just... Oh, I did write them. Never mind. I thought I wrote these as fractions, but I prefer to write them as powers. Okay, so taking the the determinant, we have 2x times x to the minus 2. That's going to be 2 over x minus, but then we have this minus sign here, so that's going to make a positive. And I'll go ahead and multiply. Negative 3 plus 2, when we multiply these 2 powers x, we get an x to the minus 1. And so what do we get total? 2 over x plus 2 over x, so 4 over x. That's the wronskian. So 4 over x is what goes in place of this denominator. And so let's find W1 now. W1 looks like the wronskian, but the first column gets replaced with 0 and x, the non-homogeneous term in our differential equation. So I have 0x, and then up here I have x squared 2x. And divide by the wronskian, divide by 4 over x. So rewriting this u1 prime equals, okay, that's really x over 4 when we divide by that fraction. And this determinant is 0 times 2x minus cubed. So that simplifies to minus 1/4 x to what power? X times 1, or x to the first, x to the cubed, so x to the fourth. And that's very easy to integrate. Negative 1/20th x to the fifth power. Antiderivative x to the fourth is 1/5 x to the fifth. Oh, okay, so that wasn't that bad. Now let's find u2. u2 prime equals, we have our W2 over our wronskian, which again was 4 over x. So I'm going to write 4 over x is x over 4. And now I need to find W2. W2 looks like the wronskian at first, x to minus 2, negative 2x and negative 3. Negative 2x and negative 3. Oops, negative 3. Now here we need 0 and x. And that is going to be, what do we have? 1 over x minus negative, oh, no, minus 0. Minus 0. So this is just, this is multiply this 1 over x, that cancels that x, so we get 1/4. So the u2 is just quarter x. Okay. Hold it down there. Noise. Okay, so c1 x to the minus 2 plus c2 x squared. And now we just write our u1, which was this. Negative 1 over 20 x to the fifth times. Now here you have to be careful. Make sure you don't flip the order of x negative 2 and x squared. Otherwise, you make a mistake right at this step. First function was x to the minus 2. And then we have plus 1/4 x. That was our u2 times x squared. Okay, you'd simplify this. Here it's interesting. We get minus 1/20th x cubed plus 1/4 x cubed. So you can combine these terms. It's some constant times x cubed. I'm gonna skip that. But the important part is that constant times x cubed is not one of these two terms, so that can't get absorbed into any of these. So then you just do some simplifying, and then that completes that non-homogeneous Cauchy-Euler problem. Okay. Any questions, anyone? Okay, so that concludes this review session. Thank you very much for for participating, showing up, asking questions. Again, apologize about the technical difficulties in the beginning. If we do this again, though, I think it'll go much smoother. So I will see you all on Tuesday. If you think of any questions at all or get stuck on anything, feel free to email me, and I will respond as soon as possible. Enjoy the rest of your Sunday afternoon.
Thanks.